Hi, welcome to the Signal Pad. I have a very special episode for you guys today where my brother finally has managed to join in one of the videos. Even though he hasn't been in the previous videos, he's always been behind the scene working and maintaining the website and the blog. So he's always been doing something for the website. He also has a PhD in electrical engineering. We actually have a really similar background in high-speed ASIC design, and we're going to talk to you about a very interesting topic. So I'm going to let him open it for you.
Yeah, so today we thought we'd look at transimpedance amplifiers and go through really with a detailed analysis of a very simple circuit, but characterize the gain and the behavior while using theory and then looking at measurements to see how they match up.
Yeah, as it is very customary on the Signal Path, we like to take a very thorough approach. So we want to show you really from the deep understanding that is required to truly understand these circuits. And this is a very simple one. It's actually deceptively simple, this transimpedance amplifier, but there's a lot of cool things to learn from it. So let's get started. So what I'm interested in doing is taking a block that you're all very familiar with, such as this CMOS inverter, and using it in a very different way. And I'm sure you've all seen the CMOS inverter before. All it does is that it takes a logic value 0 at the input and converts it to a 1, or a logic value 1 into a 0. And that essentially means that a voltage of 0 volts will give you an output of VDD, and VDD will give you 0. Now if you take a look at what's inside an inverter, we can further understand how it can be done.
So on the right hand side, we're showing the schematic implementation using an NMOS and PMOS device. Now what we want to do is, instead of just putting either 0 or VDD on the input and getting an inverted version at the output, we'll actually go ahead and put multiple different values at VN, so all the way ranging from 0 to VDD, and then look at what the output is. Now if this is biased correctly, so for certain values of VN, we can actually use this inverter as an amplifier. Now I want to investigate that through measurement so we can really appreciate what's going on. And in order to do that, we're going to use an IC called the ALD1105. And this is nothing more than 4 transistors in one package. And it has 2 NMOS devices and it has 2 PMOS devices. Now because of the different strength between the NMOS and the PMOS, due to the difference in the mobility between holes and carriers in a device like this, we're going to have to use 2 PMOS devices in parallel and 1 NMOS device by itself in order to get a symmetric behavior in the inverter. So let's go ahead and put it on the breadboard and actually measure it, and then we can take a look at the IV characteristic and draw some conclusions. So here's our setup for measuring the CMOS inverter. There's a lot of stuff on here. What did you build? Okay, so let's ignore most of this for now. The only thing we should look at right now is this chip right now. So that's the ALD1105 chip that we showed. And this is basically the input and output of our inverter.
So by putting a voltage sweep at the input of the inverter and measuring the output voltage and characterizing all of that on the instrument, then we should be able to do some of our calculation. And for that, we're going to use the Keithley 228OS-32-6 as our power supply. This is what's going to give us the 10 volts on our inverter. And of course, for sweeping the input-output, we're going to use pretty much the industry standard Keithley 2450 at the top and Keithley 2460 at the bottom. So the 2450 is going to apply the gate voltage at the input of the inverter, and the Keithley 2460 is going to monitor the output voltage. And we're going to use the Kickstart software in order to be able to do this sweep and capture all the data. So let's move to the Kickstart software. Here we are on the Kickstart software. You've seen this before. I did a full review on the 2450 and the 2460 and the DMM from Keithley. Definitely worth watching. Lots of cool experiments in there. So here we have just simply configured the SMU1 to sweep from 3.75 to 5.25. Now this is around the middle point of our power supply. That's where we expect the inverter to have the highest gain and will be the most linear. So it's going to sweep from 3.75 525 with a 10 millivolt resolution, and the second SMU is simply going to provide 0 amp of current and just measure the output voltage. This is one way of getting a volt-volt transfer function of the inverter. So let's go ahead and run it and see what happens. Here we go. Now the instrument is going to do all of its sweep, and we can go under graph and you can see that it is indeed doing its sweep. Now the Kickstart software doesn't do a very good job at handling large amount of data, but you can see that it's showing all the different voltages that are being plotted, and as if you pay attention, you see that the output of the inverter is slowly going down as the input to the inverter is going up. So you can see, and we're almost at the middle of the transfer function there, and it should become very clear very soon, and there it is. Look at that. It looks pretty good. And you can see that over here will be the logic value 1 at the output, and over there will be the logic value 0, and right here is where we are interested. But it's difficult to look at it on this software and do analysis on it, so let's grab the data and take it out. Now there is also another way of doing this, a measurement, instead of having to use the Keithley source meters, but if you want to do it in a transient effect. Now that's not entirely preferred because that is really a transient behavior, not a DC characteristic, but if the frequency is low enough and the inverter is fast enough, it is a good approximation. So in this case what we've done is that we're using the Siglent a function generator here to generate a triangular wave, and we're going to feed that triangular wave into the CMOS inverter. The reason we're using a triangular wave is because we have a linear input change being applied to the input of the inverter, and it allows us to see what the output characteristic looks like with a linear input. So the setup is essentially the same. I'm splitting the output of the function generator into two, so one of them will go into the scope and the other one goes directly to the input of the inverter, and the output of the inverter is taken out so we can also look at that on the scope. Everything else is the same. We have the same power supply powering our inverter over here, and you can see that we have a 1.8 milliamp power consumption, and the reason that's there is because that's the dynamic power consumption of the inverter during this operation with a triangular waveform at its input. Another thing to note is that the frequency we're using is 1 kHz, so we know the slope at the of the signal at the input of the inverter. So let's look at the oscilloscope and see what happens.
So here we're using the Keysight S-series oscilloscope, and on channel 1, which is the yellow waveform, we're looking at our input which is the triangular wave, and as my brother explained, that's at 1 kHz with a 10 volt peak-to-peak amplitude. And on channel 3, which is the blue waveform, is our output of the inverter. Now one interesting thing to look at here is that this blue output isn't perfectly symmetric, and that's because of the fact that the NMOS and PMOS devices were using discrete transistors and they're not perfectly sized to give us a symmetric output waveform. So what we can do with this is we can go ahead and we can use an XY mode on this oscilloscope. So what this does is it takes one channel and plots it on the x-axis, and then for each value it plots the corresponding y value using another channel, so channel 3. So this gives us the transfer characteristics, which is the same thing that we were able to get from the Keithley source meter. Now one other thing we can do is we can go ahead and add a math function and take the derivative of the output, and that'll give us some additional insight into the gain of this inverter.
So by essentially taking the derivative of channel 3, we can see the slope of the output of the CMOS inverter. And you can see that obviously where the slope is the sharpest is that has the highest value, and this is where we are interested to use it as an amplifier. The function that calculates the derivative has peaks, so you can see as a positive peak here the gain is positive, as a negative peak here the gain is negative, and so on and on. And by this we can find out what the slope is. And why would we bother with that? Well, if you want to find a gain of this, you have to calculate the slope of this curve right here. But that's difficult to calculate in this form, so this is another way of doing that. Now the input is known to us. We know it's a 10 volt peak to peak, 1 kHz signal, so the slope is known. That's 20,000 volts per second. That's the slope of the input. And the slope of the output, the instrument is calculating, and it has a maximum value of 375,000 volts per second. And if I divide those two numbers, I get almost exactly 18.8 volts per volt be the gain of the CMOS inverter at that transition point. So let's take all this data back to the computer and take a look at it.
So all we've done here is taken the results from the Keithley Kickstart program and brought it into a nice format here. So here we're showing on the x-axis on this plot, we're varying the input voltage, and then on the y-axis we're looking at the output voltage. Now we're only showing a small portion of the input voltage. We don't go all the way between 0 and VDD. Naturally, if we put 0 volts at the input, we expect the output to be inverted and be at 10 volts. Similarly, if we put 10 volts at the input, we expect the output to be at 0. But what we're really interested in is this region in the middle where we have a linear behavior. So what we can do is if we bias our inverter right at this point and we put small signals around that bias point, we actually get a linear behavior, so we can get some gain out of it. And we've done some fitting here, and we can see that the slope of this line is actually 18.8. So that's the gain of our inverter. We can get a gain of minus 18.8 volts per volt out of this if we bias it at the right point. And it's also important to point out is that the transistors in this inverter go through various regions of operation. So that when the input is really small at 0 volts, for example, then the NMOS transistor is completely turned off and the PMOS transistor is in deep triode. That will be all the way at the end of this graph, which we are not showing, where the output would actually be 10 volts. And vice versa, if I increase the input all the way up to 10 volts, then I turn on
the NMOS device really hard, deep into triode, and then the PMOS device will be turned off. Digital designers who use this inverter for digital purposes operate it either in this region or operate it all the way out in this region. We want to operate it in the middle when both of the devices are operating in the active region. And that is the trick to be able to use an inverter as an amplifier. So it's nice and great that we managed to measure the gain of this amplifier using two different methods, the Keithley source meters as well as the oscilloscope method. But what is ultimately important is to be able to derive an equation that represents the small signal gain of this amplifier based on device parameters. That's ultimately what you want to do in order to be able to do some analytical work on this when you're designing circuits later on. So how do we do this?
So basically, if we bias this inverter right at the middle, where we're in the linear region, both transistors are in saturation, and we essentially have two common source amplifiers. So what we can do is use a very powerful tool, which is superposition, to kind of break it up and find the gain of each one at a time. So I always tell my students that if you have no idea what's going on, the answer is almost always use superposition, because it's such a powerful tool and it shows up a lot. So for example, on the left hand side, we're looking at the NMOS common source. So in this case, the NMOS is doing the amplification, and we're just showing the output impedance of the PMOS, which is ROP. So then our gain for this common source would just be the GM of the NMOS multiplied by the output impedance, RO, and in parallel with ROP. And of course, it's an inverting stage, so the gain is negative. Similarly, we can do the exact same thing for the PMOS common source, and again we get the gain that's now the transconductance GM of the PMOS multiplied by the output impedance. So finally, the total gain is the sum of these two. Again, we use superposition, so we get the sum of the GMs multiplied by the output impedance.
So this is really an interesting effect that's happening here, because it means that both the NMOS transistor and the PMOS transistor are contributing to the overall gain. So we're actually getting more gain as a result of the fact that both of these devices are active at the same time. So this is going to definitely increase the gain of the circuit. Now, having said that, if you look at this equation, we're talking about GM of the NMOS, the GM of the PMOS, the output conductance of the NMOS and the PMOS. We don't have any of these numbers because we don't have the small signal parameters of these devices. So in the real world, what do? Well, in the real world, you would have to go look at the data sheet and extract these parameters. But what if you're inventing a new device? What if you're making a new transistor? Then you have to go ahead and measure the characteristic of the transistors and then extract the small signal parameters. And this is a link that is most not well understood by the people who are learning this material for the first time. The link between DC characteristic of the device, which leads to small signal parameters, which can be used to calculate gains of amplifiers. So let's go ahead, measure the DC characteristic of these devices using the Keithley source meters again, and then extract these parameters out, which will be a really interesting thing to try.
Just another point that I want to make is that this transconductance and output impedance of the transistors depend on the device parameters resulting from the chemistry and the physics. Now, we don't know any of these parameters, so we need to go ahead and figure out these GM and RO based on measurements from the actual device.
So we're here once again. This time my brother has wired up for the NMOS transistor to be measured its IV characteristic by varying VDS and at discrete values of VGS. So we have to go back and use the Kickstart software again, because we're doing exactly the same thing. We're going to use the Keithley 2450 and the 2460. The Keithley 2450 is going to be used to sweep different VGS values, and the Keithley 2460 is going to apply different VDS values and measure the current through the transistor. So this is going to measure the drain current, it's going to apply the gate voltage, and we should be able to get some really neat IV characteristic from the devices. And here we're once again using the Kickstart software, and this time we're measuring an NMOS transistor. Here on the SMU1, we are sweeping the VGS of the transistor from 1 volt to 10 volt every 0.5 volt step. So this is going to give us discrete curves where we can vary the VDS. And on SMU2, we're going to vary the VDS from 0 to 10 volts at 0.1 volt steps to give us a nice fine resolution in order to be able to calculate the output conductance of the transistor. So I'm going to go ahead and run this test. Now we're going to get our sweep started, and if I go under the graph, you're going to be able to see it's already started. Right over here, the transistor is starting to be in triode region, and you can see that it's going nicely into the active region and is flattening out, and this curve is still continuing. And here's another value of the VGS, and as to be expected, the current obviously continues to go higher and higher because you have a larger VGS value, and once the device is turned on, you're going to be able to get more current. And here's yet again a third value of the VGS, and look how flat and nice these regions of the VDS are, and that's how you're going to calculate the R naught. Now we're going to do this for the NMOS and for the PMOS. We're going to get a whole family of curves, bring them back to the computer again, and look at them and help us calculate the value for R naught. So I'm going to let this run. We're going to go back and take a look at it. So again, what we've done is we've taken the measurement that we did on the Keithley source meters for the NMOS transistor and for the PMOS transistor, and we brought them into this nice plot so we can take a look at it. And look at these plots. They look exactly like what you would expect from a textbook, but these are actual measured results from the devices we have in the lab. And this is the amazing, powerful tool of being able to close the gap between theory and measurement. Now, if you look here at the NMOS device, you can see at the very, very left corner here, when the VDS is really small, the device is in triode. And at the very, very bottom, when the IDS is equal to 0, the device is turned off. And once you increase the VDS, you can see here where the lines look mostly flat, that's when the device is in the active region. And then you have the slope of these lines, which then would represent the output conductance R naught of the device itself. And for the PMOS, you have exactly the same thing. Now, Shayan can tell you why do these look different? What is going on? Why do these values don't match each other?
This is because, again, we're using these discrete devices, and so as we said earlier, we have one NMOS device from the chip, and we're using two PMOS devices in parallel to increase the strength. But even so, the sizes are they're not sized appropriately, so they don't have the same amount of strength. Even though we've used two PMOSs in parallel, it's still not as strong as one NMOS device. That's why the currents are smaller.
Yes, so the mu NCox W over L of the NMOS is much bigger than the mu PCox W over L of the PMOS. So therefore, for the same amount of VGS, you're going to have different amounts of current going through these devices.
So we have a lot of curves here. We have many for the NMOS and many for the PMOS. How do we know which one we should pick? So as we saw earlier when we did the transfer characteristics of the inverter, we saw that it was most linear when the input and output were at 4.5 volts, as we've shown here. So that corresponds to a VGS of 4.5 volts for the NMOS and a VSG of 5.5 volts for the PMOS. So that tells us which of the curves we need to be looking at, the ones that correspond to the appropriate VGSs. Now, again, since our output is also our 4.5, we also know what our VDS voltage should be. So that's the point that we're highlighting. Now what we need to do is take the slope at that point, and that will correspond to the output resistance. So again, we've done a DC characteristic here of the transistor, and by taking the slope, we're getting the small signal parameter. So in that small region around the operating point, it's acting like a resistance, and we calculate the slope. So for the NMOS, the resistance is 14.1 kilo ohms, and for the PMOS, it's 12.5 kilo ohms.
Now if there's one thing that I want you to get from this video, is to be able to understand the important relationship between the DC operating point and small signal parameters and how they're closely tied together. And this is why we did this experiment. Now that we know what the RON and ROP is, we can go back and look at this equation, and in fact you can extract the parameter lambda from this, and this is typically one of the ways that a parameter such as this is extracted by doing the DC measurement on the device themselves.
Now one other thing I want to point out is the reason we call this a small signal parameter is that slope is only really accurate in that small region. If I start to go further and further away from that operating point, we can see that obviously it can no longer be approximated by a straight line. So that's why we use the word small signal, right? The input needs to be within some range for it to be able to be approximated with a straight line.
Right, and if you go beyond that range, then the device becomes nonlinear, and that's a whole different discussion on analyzing the large signal behavior. But for now, we're focusing only on the small signal. So once again, we have to run another sweep in order to be able to extract the transconductance of the device. This time we have to sweep the VGS of the device in a much more fine step so we can extract that parameter with more accuracy. And here you can see that I'm sweeping the VGS from 0 to 10 volts at a 50 millivolt step, which is pretty nice. And on the drain voltage, I'm keeping the drain voltage constant at a 5.5 volt. Now this is for the PMOS device, and that's why the drain voltage is 5.5 based on what we showed the operating point we would like it to be. I've already ran this, and take a look. It looks very nice, and you have to look at it from up here because it's upside down because it's a PMOS device, but you can see starting at no current. This is 0 at the very top, and you can see the quadratic behavior over here. Now I'm going to explain that with my brother on the other slides once we get back to it, but let's take all this data and take it back to the PC again. So once again, we've taken the data we collected from the Keithley source meters for calculating the GM back onto the computer. And here we have the equation for the GM once again. And the slope of the IV characteristic will give us the GM. And look, we've plotted it here for the NMOS, and we've plotted it here for the PMOS. Now if you look, obviously, what do we expect? We expect a quadratic relationship between IDS and VGS. And in fact, if you look here, you can indeed see that there is a square square law behavior, and then this is our operating point. This is our VGS 4.5 volt as we discovered before, and that is corresponding to exactly the current that we measured on the power supply. Now, if I take the slope of this, I will get a GM of the NMOS device to be 1.69 millisiemens, and we do exactly the same thing for the PMOS, and with the PMOS GM is 1.13 millisiemens. Once again, we can see that the GM of the PMOS is smaller than the NMOS. That corresponds to the lower mobility of the holes compared to the electrons. Now, this of course also is backwards because we have the VGS of the NMOS transistor and the PMOS transistor is different depending on how you want to plot it. But there's also another thing to note is that this curve doesn't maintain the square law behavior all the way for very large values of VGS and for very large values of VGS for the NMOS. And this is due to the mobility degradation of the device. You can actually degrade the mobility of the carriers in an NMOS and a PMOS so much that, that increasing the VGS no longer gives you the square law region, and it ends up being linear. And if you look carefully, in fact, it starts degrading. But that's a topic for a whole different episode. But for now, let's focus on the fact that we have extracted once again from the DC operating point, from the IV characteristic, the small signal parameters required in the equation for the gain.
And again, another repeating ourselves, it was the same thing that we did for RO. Our transconductance is only valid within some range around the operating point. If we deviate too far from that, again, we can no longer approximate it with a straight line, and we can't just take the slope simply. Okay, finally, we have all the parameters we need to actually look and calculate the gain analytically. Now, just before we do that, we noticed when we did the transfer characteristics early on using measurements, we got a gain of minus 18.8 volts per volt from the inverter. Now, let's go ahead and plug in our transconductance and output impedance that we just measured and figure out what the gain is. So we plugged everything in and we get a gain of minus 18.6 volt per volt, which is remarkably close to what we measured on the instrument. And this is of course the power of being able to measure the device parameters. This is really valid, and it confirms everything that we said about the equation. So we know that our equations and our parameters are all correct. This is quite an amazing thing to be able to replicate. And another thing that's very interesting is what this cat likes. It's a massage.
So we talked so much about calculating the gain of this amplifier and analyzing it, but the whole point of the video was to make a transimpedance amplifier. And a transimpedance amplifier is an amplifier that converts current to a voltage, so it can be used with things like photodetectors in an optical communication system. And this is what we plan to do at the end, is to use a photodetector to actually be able to use our amplifier in action. But what are ways that you can convert a current to a voltage? Well, the simplest is just to use a resistor. Very straightforward. You have a current I in going through a resistor, and that will generate a voltage V out. This is just Ohm's law. So the gain of this circuit is RF. Very straightforward. But if we want to use our amplifier, we can do a trick and use it in feedback, in shunt feedback. In fact, we can connect our resistor RF between the input and the output of our amplifier, and this will have several effects. Not only will this create a transimpedance amplifier, but it will also self-bias this CMOS inverter right at the middle where we want to use it as an amplifier, because the input-output voltage will be the same since there is no current going through the gate of the devices. So it's a very clever, little simple circuit that will accomplish this for us. Now we can convert I in to V out, and the analysis of that is going to become clear. We want to find out what that gain is. I know there's a lot of theory going on, but believe me, it's worth it. There's going to be a bunch of analysis which goes at the heart of this video. Shayan's going to explain that, but please stay tuned because we're going to measure it, and it's really, really important stuff.
Like my brother said, this is really, really important stuff. It's basically a matter of life and death, so let's get to it. Here we're showing the amplifier again. So what we need to do is we need to find the closed loop gain. So essentially the gain from the input I in to the output V out. And what we have to do is we have to actually break the feedback in order to do that. So this is based on feedback theory. The closed loop gain, so that's I in to V out, is a function of the open loop gain. That's when we break the feedback and consider the loading, which I'll do in a second. And then we divide that 1 plus beta times the open loop gain. So first, let's go ahead and find the open loop gain. So the first thing we need to do is recognize the type of feedback. This is a shunt feedback, as my brother said earlier. And what we've done is we've broken the loading appropriately for that type of feedback. So that shows up as two resistors, one at the input and one at the output to ground. Now, one way to find the gain that I like to do, to find V out to I in, this is our open loop gain now, is to break it up into different steps. So first, find the gain from I in to V in, the node labeled in red, and then to go ahead and find the gain from V in to the output. So to find the gain from I in to V in, that's just simply the current multiplied by the resistance, so that gain is just RF. And then from V in to V out, well, that's what we did earlier. It's the sum of the transconductances multiplied by the output impedance. Now the only difference here is that we have this extra term RF, and that's because of the loading that the feedback network has on our amplifier. Now when we did this earlier, we found that the gain was about 18.8 volts per volt. Here we see that the gain has dropped to 15.25. This is again as a result of the fact that the loading, the RF, has an effect on the amplifier gain.
Now, there's also one other thing it's important to point out here is that we are making an assumption that the RF resistor here is unilateral. But it's not entirely true, because there is two paths for the signal I in to reach V out. One is through the amplifier and one is through the forward path through the RF. In reality, that forward path here is being ignored, and its effect is really minor anyway. But generally speaking, this equation of feedback assumes a unilateral beta network. The feedback network is supposed to be only backwards. But that's not a problem. It doesn't really have that much of an effect here. But at the end of the day, we can see that in fact we can calculate the gain of this amplifier, the open loop, including the loading effect, in this fashion. So we did calculate the open loop gain of the amplifier, but in order to really calculate the closed loop gain, we're still missing one parameter, and that parameter is beta. And we can calculate that really easily because we know the type of feedback. This is a shunt feedback, and what shunt feedback says is that I'm going to take a portion of the output voltage, I'm going to convert it to a current, and I'm going to subtract it from the input current. That's what shunt feedback does in a negative feedback. So this is very easy to calculate because we can put our test voltage at the output. Here's our feedback resistor, and here's the feedback current that's being subtracted from the input. And pretty straightforward. Again, we have Ohm's law, and we can calculate beta, and it ends up being minus 1 over RF. So now we have our value of beta. We can go ahead, plug it back into this equation. Here's the open loop gain we did calculated from before. Beta we just calculated now. Put it all together, and it turns out our closed loop gain is 28.14 kilovolts per amp, which is just kilo ohms, which is very close to the feedback resistor value of 30 kilo ohm, and that's because the open loop amplifier gain is about 15.6. is sufficiently large enough that this equation can actually be simplified to just being 1 over beta. But there's something wrong here, isn't it?
So why did we do all this? It seems like the gain is less than just using a resistor. So if we were using that first scheme, which was the resistor as our transimpedance amplifier, we would be better off, we'd have more gain. Why would we ever do all this?
And in order to answer that question, we've built this circuit. So let's go ahead, back in the lab, let's measure it and compare the difference between using a photodetector with just a resistor and using it with our own transimpedance amplifier, and the difference will become very clear.
So here we're showing our final setup. We have 2 photodetectors here and a transmitter, and we built both of the transimpedance amplifiers that we described. One of them is just a resistor that's up here, and then using this chip we've built the transimpedance amplifier using the NMOS and PMOS transistors, and we also have this RF resistor and feedback. Now the first important thing to check is to make sure that this is biased correctly. As we said, the RF resistor is going to also bias this itself, self-bias. So we can go ahead and look at the output voltage and make sure that it's where it should be, and we can see that it's at 4.5 volts, which is where we expect. Again, this is not right at the middle at 5 volts because the NMOS and PMOS are not exactly the right ratio, but this is perfect. It's self-biased, so we can move on to doing some transient measurements.
And of course, one other point is that you can see that now our inverter is consuming about 4.9 milliamps of current because it's biased right in the middle. This is now both devices in the active region. This amplifier has a DC power consumption of roughly about just under 50 milliwatts. So we are burning power in this transimpedance amplifier. As to be expected, it is a Class A amplifier after all. And now finally we have put a signal through our transmitter, our LED essentially, and then we have the two photodetectors simultaneously receiving the signal with roughly the same amplitude, and as we said before, one to the resistor and one to the transimpedance amplifier. So now we can go on the oscilloscope, take a look at the output waveform from the two different mechanisms of generating a voltage, and then we can finally measure the bandwidth, and that's where the difference is going to be, and we will explain it on the oscilloscope. And here we finally have both of the waveforms on the oscilloscope. The yellow waveform is a signal we get directly by using the resistor, and the blue waveform is coming from the CMOS transimpedance amplifier. And since both of the resistors are the same, both the resistor in feedback and the resistor we're using as our current to voltage converter, we expect the same amount of gain, and indeed that's the case. You can see these two signals have 2 volt peak to peak of amplitude at a frequency of 100 Hertz. And both of the photodetectors are receiving roughly the same amount of light, so we expect the same signal. So let's go ahead and increase the frequency and actually see what happens. Now remember that 2 volt peak to peak, in order for us to measure the 3 dB bandwidth, we're looking at the magic drop of the square root of 2, so we're looking at this signal reaching 1.41 volt peak to peak. At that point we have hit the 3 dB bandwidth. So my brother is going to increase this and let's see what happens. So we're at 100 Hertz now, 200 Hertz. We're going to continue going up. You can see that the yellow signal coming from the resistor is already shrinking. Oh, there we go. We actually hit 1.41 right already. And so that means that the 3 dB bandwidth using the resistor solution is 1.41 volt peak to peak. Here it's at, what is that? 1 kilohertz. There it is. At 1 kilohertz, we're hitting the 3 dB bandwidth. And this is to be expected because the 30 kilo ohm resistor we're using combined with the capacitance of the photodetector is going to give us this type of bandwidth. But take a look. The blue waveform is still at 2 volt peak to peak. It's not even close to its 3 dB bandwidth. So let's go ahead and increase and see what happens.
So let's keep increasing while we change the scale on the oscilloscope so we can see the signal still. We're at 5 kilohertz now. We're still only at 1.7 volts peak to peak. Keep increasing, hitting 10 kilohertz, still not at the 3 dB bandwidth. And right around here we're hitting our 3 dB bandwidth now, 11.8 kilohertz.
Yeah, and take a look. The yellow signal is at 200 millivolt peak to peak. This is almost completely dead, but the signal coming from the transimpedance amplifier is now finally hit this 3 dB bandwidth, and the 3 dB bandwidth is 11.8 kilohertz. So we had 1 kilohertz from the resistor solution, but 11.8 kilohertz from the transimpedance. It's a factor of 11.8 improvement in bandwidth, which is extraordinarily large for this type of solution. Now, of course, this is not coming for free because as we said before, we are burning 50 millivolt in the transimpedance amplifier. So why does this happen? Well, as the last closing remark, let's take a look at the equation that explains that behavior, and then we're done.
Now let's go ahead and look at what limits our bandwidth. For the case of just using a resistor for our transimpedance amplifier, we will have the pole caused by the capacitance of the photodetector, and again we can see the capacitor appears directly across RF, so that's what will set our bandwidth. But if we go ahead and look at the transimpedance amplifier, again in this case we'll also assume that the dominant pole is at the input and caused by the capacitor of the photodetector. Now the difference is that now this capacitor appears across the resistance looking into this amplifier, which is lowered by a factor of 1 plus beta A due to the shunt-shunt feedback. So now that's what gives us such a higher bandwidth. The resistance looking in is actually much smaller than the case of just using RF by itself.
Now, this is a very interesting effect because this means that we should have 1 plus beta A increased in bandwidth. Now, we don't have exactly that much. We have about a factor of 11.6, maybe a factor of 12. We should in reality have a factor of about 15.5. That was the loop gain of the amplifier with the feedback as we described earlier. This means that we're not exactly matching the theory, and there's 2 reasons for that. And we're going to leave those 2 reasons for you to discuss in the comment section, and we'll be very interested to hear what you guys think. Now, we've been talking about the PMOS and an NMOS and a resistor for so long, and we've just barely scratched the surface. Remember, we didn't talk about the higher frequency model of the transistor, we didn't talk about large signal behavior, we didn't talk about device physics and device chemistry and how devices are actually manufactured, we didn't talk about noise at all, which is a huge topic in itself. This is just barely touching, scratching the surface of analog electronics, and that's what is really interesting about it, because there's so much to learn. Now, we put a lot of effort in this video, and I hope that you guys enjoyed it. This was fun for us to make as well, and we would love to hear what you guys think. If you like it, give the video a thumbs up and share it with other students in university who might be able to benefit from this. So, until next time.